All right, class, I'm going to try a video solution here. Let's see. It's an uncertainty principle. So keep in mind that the uncertainty in the position multiplied by the uncertainty in the momentum must be greater than or equal to h over 4 pi. And maybe as a side note, sometimes we like to put what we call h bar, the reduced Planck's constant, so that h bar is h over 2 pi. And I noticed your book touches on this. I kind of stopped short of that and said, well, maybe this is a good place to stop our introduction to modern physics just with Planck's constant and the 4 pi and not worried about this new symbol. The h bar is not a big one, but as long as I was making the video, I thought maybe I'll throw that in there here. But anyways, it says, use the uncertainty principle to show that if an electron were confined inside an atomic nucleus, the diameter of 2 times 10 to the minus 15th, it would have to be going relativistically. So, by the way, this is kind of the physics argument of why the atom is the size it is because if you get this too small, or the smaller you get it, then the bigger this one gets. And then if it gets too big, it goes so fast, it has so much energy, it's not confined. That's not its lowest energy state. So the electron wants to spread out because of this fact. Now, it wants to get pulled in because of the positive and negative charges. And the size of the atom is the perfect balance in between it. And so that explains why our atoms have a certain size. And that's really the gist of this problem. It's trying to go down that road of really trying to show you why an atom is the size it is, why the proton in the middle, which has a size of 2 times 10 to the minus 15th, will not pull the electron in to that tight little space. The electron will actually be a wave really far out. This is something like 100,000 times bigger. And so it pulls the electron in, but only to a limited amount. And so it is that balance where the lowest energy exists. If you, like I say, if you pull it in too much, you have too much kinetic energy. And of course, you let it go out, then it has too far away and it has too much potential energy. And so this is the lowest energy state. So it's the natural process of why the atoms are the size that they are. All right, so I digress a little bit from this problem, but that's really the gist of the problem that the author wants you to see here, is about how the uncertainty principle is. So if you do this, you could say that the unknown momentum has to be at least, and then if I take this h over 4 pi and divide it by, say, its diameter. So this is the 6.63 times 10 to the negative 34 joules second for Planck's constant, divided by 4 pi. And then if you take it being trapped within the diameter, 2 times 10 to the minus 15 meters, you get a momentum of this thing, an uncertainty in the momentum. So that means the momentum could be at least that much and maybe more, but at least that much and maybe I'll do my units first. If you remember, a joule is a kilogram meter squared over second squared. So if I multiply by a second and divide by that meter, one of the meters go away and one of the seconds go away. And I get the conventional unit of kilogram meters squared for the momentum, and technically the uncertainty of the momentum. So this position, as I said, is so small that this is actually really high and would constitute a huge speed, which would constitute a huge amount of kinetic energy, which is why the electron would rather move out and thereby having less kinetic energy, although more potential energy, but still being overall less energy. So 6.63 times 10 to the negative 34 is the h, divided by the 4, divided by the pi, divided by the 2 times 10 to the negative 15. So we're looking at an object of an electron that if you were to cram it into this little tight spot here, it would have to have an unknown momentum of this much. So that means it has at least this much, because it would be, 0 plus or minus this amount, or maybe some value plus or minus that amount. So it has at least that much. And if you want to go out stationary, I think you could say that the momentum's 0, but it's like jumping around here with a lot of uncertainty in its momentum. Okay? Now, for an electron, then, let's look at the momentum. Let's just say, for the sake of argument here, that it's 0 and then plus or minus this amount. Let me just set that on momentum, which if we use classical physics, if we set it to mv, remember that is how we first learned momentum, but now we're learning it was more complicated than that. It's gamma mv, and anything that is about less than 10% of the speed of light, gamma is approximately 1. So that's what Newton and Galileo and Kepler and Joule and all those early scientists on mechanics, that's what they did. They were discovering the low speed physics, what we now call classical physics, when gamma is equal to 1. So to see if this even makes sense, watch this. Let's take and use the classical equation. And so we've got this for our momentum, and if we divide it by the mass of this electron, 9.11 times 10 to the negative 31, we would get a speed of this electron as 2.75 times 10 to the 10th meters per second. And I laugh because 10 to the 10th, this is 100 times greater than the speed of light. And so clearly, this must mean we are relativistic speeds. This would be an inappropriate way, just saying momentum equals mv, to calculate the speed of it, because this mv is only true for less than 10% the speed of light, which is about 3 times 10 to the 7th, and we are pretty close to 3 times 10 to the 10th. So we're 1,000 times greater than this equation is valid. So certainly, this number and this calculation is kind of meaningless, other than it tells us right away that I think what we want to know, we could probably stop actually right there, because it says it would have to be moving relativistic, and it says use the uncertainty principle. So right there we just know that it would be relativistic. We got an equation that would be way above 10%, so we would argue that this equation is not even valid. So I would have to say this is not actually the speed, but I would have to say it is proof that I'm way above 10%, and so we are relativistic. But I noticed that the author in the solutions went on to calculate the speed. So I will too. I think I'll do it a little different. The solution guide uses the relationship between energy and rest mass and momentum. I'm going to go ahead and just use the momentum equals gamma mv, and then calculate that for the speed. So let's basically do the same thing, but this time instead of setting it equal to mv, let's set it what it should be equal to all the time, and must be set equal to when we're talking about relativistic speed. So let's use the gamma mv here. And so using that same amount of momentum, the 2.51 times 10 to the minus 10 for the momentum, maybe putting the v and gamma together, although I'll write the gamma as 1 over the square root of 1 minus v squared over c squared. And I'll move the m over to this side. So let's see, there's the v, there's the gamma. Move the m over to here, 9.11 times 10 to the negative 31. And to get rid of square roots, I will square everything. So this will be a v squared, 1 minus v squared over c squared. And so I'll begin to solve for v. And over here, let me get a number to work with. This was 2.51 times 10 to the negative 20, divided by 9.11 times 10 to the negative 31, and, oh, I guess that's the number I had. I didn't have to do that again. But now I'll take the square of that, and so we're looking at 7.59 times 10 to the 20th. Now, maybe just to give me something to match here, let's do a v over c squared. So divide both sides by c squared. So divide, and get a number here, 3 times 10 to the 8th squared. Okay. So this is 8,435. All right. Now bringing this over, I would have v squared over c squared equals, and so this would be 8,435 minus 8,435 v squared over c squared. And move that over to here. We would have 8,436 v squared over c squared equals 8,435. And I can then solve this for v by taking this 8,435 divided by the 8,436. Take the square roots, move the c over, and it looks like we're looking at 0.9999. And I'm not sure I carried enough significant figures to make that valid, so I'll just go 4 nines C. So, again, hopefully, without question, we are looking at an enormous speed here, which I'll say it again, we're answering the question again, that this would have to be relativistic. It has to be greater than 10% the speed of light. But again, I think we've already proven that. We didn't have to go that far. But again, just so you can kind of see maybe the underlying foundation of this problem, you'll see now why nature does not have the electron get pulled in to something as tight and as small as the nucleus of an atom. It just would have this enormous speed, which would correspond to a lot more energy than if it stayed out. And so it's trying to find a balance point between being squeezed in because of the electrical force, and then, of course, then flying out because of the uncertainty principle, giving it a high amount of kinetic energy. And that balance is the size of the atom, and so that's why we have the atoms of this size. If nature had not had this uncertainty principle, then things like electrons would get pulled in. You wouldn't have atoms, and you wouldn't really have the world and the universe as we understand it. And so the uncertainty principle is sometimes we refer to this as a quantum pressure that pushes the electron out. It keeps everything from all the positives and negatives from just pulling each other together and collapsing the whole world as we know it on top of each other. And so it's got an important function in making atoms as we know them. Couldn't exist if it wasn't for that uncertainty principle. So there's something deep here that maybe you could have easily overlooked here. But anyways, there it is. It would have to be moving relativistically. Where then it says, whereas the proton is fine to be confined to this radius. And again, this is kind of the same argument here is, why is the proton then the size that it is? And again, it's the same answer. If it got pulled in any more than that, it would have such a large amount of uncertainty, its momentum, and such a large amount of kinetic energy that it would fly out. It would want to be out. And so it's balancing itself, being pulled in because it's being all pulled together. And if you know a little bit more about atomic physics, the protons are made out of these things called quarks, and the quarks are pulling each other in, and so they want to get pulled in. However, the uncertainty principle wants to push them out, and they meet a nice balance point, and that's the size of the nucleus. That is this 2 times 10 to the minus 15th, and it's all because of back here in this calculation where we put in the mass. And so something with a smaller mass like the electron, its balance point will be pretty big, and something with a bigger mass like the proton, it's going to be tighter in. And so the proton gets up at a set position, that is its lowest energy state, whereas the electron, which is the size of the atom, is at a 100,000 times bigger state. And that kind of explains why protons are the size they are and why atoms are the size they are. It's right here in this problem. All right, but let's maybe not dive too deeply into the whole atomic physics and why the things are the structure they are. That would be actually a fun discussion if we had more time in this class. And I think your author carries that out in about chapter 45, 46, somewhere in there. But this is the foundation of that right now. So let's come back to this calculation and do this all again. In fact, well, let me put the momentum, because when we do the proton, the uncertainty principle is still going to be the same. If you'll notice back here, the uncertainty principle had nothing to do with the mass. So we're still going to get this uncertainty and momentum. But then when I set the momentum equal to mv, and let's just try our first step where gamma is approximately 1, let's see if that's even valid. See, now the mass is 1.67 times 10 to the negative 27 kilograms. So grabbing my calculator, 2.51 times 10 to the negative 20, and divide it by 1.67 times 10 to the negative 27, I get a speed of 1.50 times 10 to the 1, 2, 3, 4, 5, 6, 7. And that's definitely less than 10% the speed of light. 3 times 10 to the 7th is 3%. Looks like we're half of 10%. So this is roughly 5% of c, which justifies that we can set gamma pretty close to 1, which justifies us getting a speed. And so there's our answer, that it is non-relativistic. Like I said back here, this was our proof already that it was relativistic, but to actually get its speed, we'd have to go through this calculation. Here, this proves that it is non-relativistic, and to get its speed, we don't have to do another calculation. We could do that same calculation, and it would just be a lot of math only to show that we would get a speed very, very close to this, because gamma is very close to this. It might be off by a few places in this decimal place, but other than that, it's the proof. And I think we can stop there. I see your author stops there. So that would be the proof that it would be non-relativistic at that point. Because again, once that thing squishes in so much that it gets to be relativistic speed, it gets to be too much kinetic energy, and you might say it explodes back out. So that's why, again, the proton will not get smaller than this, and the electron will not, or the atom will not get much smaller than that. Or the electron won't, which is what's going on in the atom. All right, hope that helped.